Hello and welcome back to physics. We're studying waves, which, as you know, are disturbances caused by the vibrations of particles in a medium, sending energy from place to place without themselves moving. We've made some measurements of various properties of waves, like amplitude, wavelength, frequency, and others, and looked a little bit about what those properties mean about the motion and effects of the wave. What I'd like to do today is explore something new called a wavefront. Wavefronts are a way of interpreting more interesting waves than we've seen so far. So far, it's been pretty basic. Take a rope, give it a wiggle. You see a pulse move from left to right, like you can see here. That's kind of easy to visualize. It's sort of easy to diagram out and kind of understand. But in real life, most waves are two or even three-dimensional in nature, and that's a little trickier. So let's take a look at this picture on the lower right. You can see it's supposed to represent the flat surface of a pond, which we're going to drop a pebble into. You know what happens if you drop a pebble into the pond. It gets wet. But also, we're going to see some waves radiating outward from that spot where the pebble landed. Those waves are going to go out in a circular fashion, in concentric circles around the center, and that diagram is supposed to show that. Dark blue being the crests of the waves with the light in between being the troughs. So what can we do with that? I mean, first of all, that's an okay way of doing it, but it's kind of hard to draw. So as you can see here, I've recreated it in diagram form using solid lines to represent the crests of each wave with the dashed lines between to be the troughs. Each collection of points which are adjacent and in phase, in other words, the circles, are called wavefronts. And they're a useful way of describing what's happening in terms of waves in a system. As usual, the pictures don't really do it justice, so let's take a look at a diagram in motion. You can see here what looks to be a longitudinal wave with waves radiating outward from the center point again, just like we saw with the pond surface. Let's pretend that's you speaking in a room. So your diaphragm moves back and forth quickly, pushing on air molecules. If you choose any air molecule in this set, you can see that it moves back and forth without actually going anywhere to transfer the energy outward from that center point. The collisions, in other words, move that energy or momentum from particle to particle, and you can see the rings moving outward. Well, the actual medium itself doesn't actually go anywhere, so the air in the room stays put. And that's the idea of these waves in general, and the wave fronts in particular. Circle waves are not the only kind we see, although they are circular or spherical are probably the most common. Another kind that shows up a lot would be the plane waves, which are just kind of linear in nature. Think about if you go to the beach, at the ocean, you've seen long lines of wave approaching the shore with crest, trough, crest, trough, crest, trough. You can diagram them the same way with solid and dashed lines to represent each one. And I'll show you some examples of that in a second. Here's another motion example, though. Again, this is a longitudinal wave, and I wanted to show you this in particular to kind of highlight something from the assignment from last week. So the large black bar on the left, again, is the thing that's making the wave. Say that's your diaphragm in your voice as you speak. So it's going to push on particles and push and move them forward. And as those particles crash into other particles and transfer energy, you can see the red lines representing the crests or the wave fronts of those waves. In between each crest is an area of not many particles. That's kind of like the trough. And that information is also encoded below it in the pressure graph. So high pressure is a place where there's lots of gas particles in one place. Low pressure is when there's relatively few. And the pressure in the room is going to go upward and downward in a sine-looking curve as the waves of your voice pass through the room. The last thing I want to look at today is something called an interference pattern. So these little black boxes could represent, say, a speaker in a room, and they're emitting sounds. On the left, you see a high frequency sound, and on the right, it's lower frequency. And we can tell the difference because a change in frequency changes the waves. High frequency meaning they're going to be coming very often, very quickly. There's not going to be much space between them, so they're much more tightly packed. On the right, you can tell that these are lower frequency waves because they're further spread apart, so it'll take longer between one and the next. And that is what it is, and it's a nice diagram on its own showing you these wave fronts. But what happens if we have a second sound source in the room. Remember that two waves can occupy the same space at the same time, and the word for that is interference. So what you see here is something called an interference pattern for both of those low and high frequency waves. And the interesting result that you get, this kind of cool radial pattern that's showing up, happens because of that interference. Anywhere you see a spot where there's two dark lines crossing over each other, in other words, there's two wave fronts in the same space, well, that means the sound waves from both sources are doing the same thing at the same time. So you're going to have constructive interference. In other words, the sound's going to be extra loud at that spot. In between those areas, you'll have spots where the crests from one wave will match up with the troughs from the next, which means that you'll have cancellation, destructive interference, and it's going to be much quieter at that spot. The same pattern shows up for both because it's the same kind of wave, although the change in frequency does change the shape of it and the size of the spacing. Finally, let's just take a look at an example in motion, because I like that better. Again, you have two sources of waves. Those are up top, emitting circular wave fronts, alternating black and white rings coming out of each one. And you can see the spots where, say, like in the center, you'll have constructive interference. You have two crests matching up and making one larger crest as those waves overlap. So in the center, the waves will be taller and last for longer. And you can see the bars, the kind of grayish zones between them. That's where you're going to have destructive interference. So it's not black or white. There's no crests or trough there because the waves are going to be destructively interfering along those lines and making the amplitude smaller. So that's wave fronts and interference patterns of two-dimensional waves. Thank you for listening. Have a great rest of your day.